Hey, don't focus on my thighs. Focus on this piece of paper. Because this is where I'm going to teach you guys. So, today we're going to be talking about limits. I don't know if you guys can see that. I'm going to lower the brightness. So, what is a limit? So, recall what a function is. So, I have a function. We call it f of x equals y. And f of x is a machine. Recall from my algebra episode, or yeah, simple algebra episode, wherein I take in a value x and then it spits out a value y. So functions are, they're represented by many things, but the most simplest way of representing them is via a formula, such as x squared plus 4x plus 4, which neatly enough factors out to x plus 2 squared. But that's not the point. The point is, functions can be represented like this, or at least they can, or at least they're best represented as formulas for a particular value x. So, what is the limit of a function? So, limits are the most basic notion of a limit is defined over functions. There are more advanced notions of limits, such as those for categories, but that's a topic for another extras episode. And we're going back to calculus. So a limit is basically what y value my function approaches as I close in on a specific x value. So I'll draw it graphically here. You'll see this in a lot of like primer videos or in like textbooks. Wherein if I have a function, it could be any function. This is like some cubic or quartic function or whatever. It could be a Taylor series expansion of sine or something. But the point is, it's just f of x. It's any function that you can think of, but this is just an example. And then I have a point over here. And then let's call that value L. Y equals L. And then let's call its x value A, or x equals A. So the limit of a function is basically this over here, at this point here. So as I close in from both sides, at least for now, as I close in, usually when we're talking about limits, we're closing in from below A and above A. So as I close in on this x equals A, the function does not exceed a certain value. So right now we'll see that the y value like goes up, 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 and then from here it goes down for a second, and then it goes up, 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 up. But you notice that the y value does not go beyond it. It doesn't go higher than y equals L. Right? As I approach from both sides. So that's why we say that the limit as x approaches A of f of x is equal to L. So intuitively speaking, a limit, it's literally in the name. A limit is a limit on how high the value of a function, or how high the y value of a function is, as I get close to an x value. But we don't quite get there. That's the point of a limit, is that we don't just directly substitute x equals a into the function to find the limit, but rather we investigate the behavior of the function as I get closer to x equals a. I'm gonna see what y value my x values approaches as I get closer and closer and closer to x equals a. It may be even infinitely close, so long as I don't get there. Okay? So you guys would usually see this. There are the borders over here, and over here, and over here. And then we call this length here between these two borders epsilon, or 2 epsilon. And then this here is 2 delta. And the reason why I'm talking about this is because we're gonna be needing that when we discuss about epsilon delta proofs. because I'm pretty sure that some of you are taking AP Calculus, and you guys are gonna be, or maybe collegiate calculus, and epsilon delta proofs are part of your lessons. So I also wanna sort of give you guys a sort of procedure on how to do those proofs. Okay, so yeah. Also, sorry for the shadow. I'm using a stool right now to record the video so that it sort of goes over my thighs. But again, focus on the lesson, not my thighs. Don't focus on this. Focus on this. All right. So going back to the lesson. So okay, what's an example? All right. So let's do it graphically for now. This is the graph of x squared. F of x equals x squared. So in the start of a calculus journey, my calculus journey at least, this relation over here was a very important key to understanding the limit. Because this relation between the formula f of x, usually when we say f of x, or maybe even, it could be any symbol, a of x, b of x, h of x, even Greek letters, phi of x, alpha of x, beta of x, gamma of x. The symbols don't matter. What this is saying is that, or what this usually denotes is a formula of x, or like some like combination or expression of x. Okay, so this crucial relation was very important. It's very important, at least in your calculus journey, because it tells you that for every x value I put into here, there is a corresponding y value. So formally speaking, every x in the domain of my function gets precisely mapped to one and only one value, y. And y can be any number, x can be any number you can think of, or any object, in fact. So this is why we call functions bijections, because if I have two sets, I'll denote them by these blobs. I know that they don't quite look the same, but if I have a one-to-one mapping, so basically these sticks are the relations between objects, so they're like relationships, stuff like that. So if an exact mapping here, when one object here gets mapped onto another object here, and then they don't overlap or they don't map onto the same object, like these two go like that to one object, no, that doesn't happen, then it's called a bijection. And I can also go the other way around, and each y would also get to be mapped to an f of each y would be get mapped to an x in the first set. And bijections are a very important concept, or at least functions at least, or bijections, because when we discuss about trig functions, or at least an extras episode wherein I expand more on trigonometric functions, because I didn't quite explain why exactly we restrict the values of the trig functions between negative pi over 2 to pi over 2. I just said that. I just stated that. I didn't explain why we do that, right? And it's because of bijections and stuff like that, maintaining the function property of trigonometric functions. Okay, so going back to the lesson, let's say I want to find the limit of this function as x approaches 2. Okay, so this is the point 2, maybe this is 1, this is 3, 4, that doesn't matter right now. We just want to focus on the point 2, and we want to find out the value that the function, or the number that the function does not go beyond or greater than as I get close to 2. So I'm trying to find this L over here. What is L over here? So of course, you'll notice that, okay, so if I go beyond 2, right, the corresponding y values, okay, that's nothing already. You want to disregard those y values, so practically that's nothing, and then you want to disregard these y values over here. So you don't want to plug x values below 2 or above 2, because, well, they're not 2, that's one thing, and that we're not approaching those values, so we don't want to plug those values. But really, the simplest thing you can do, especially if you're given a polynomial like x squared plus 4x plus 4, or maybe a trig function like sine x, right? If you're given those kind of functions, the best thing you want to do, or the first thing you want to do when you're trying to find the limit with a certain number, is you just plug the value in it. So in this case, and you'll see with the calculator using the tabular method, which is usually very computation intensive because you have to evaluate a bunch of values as you get closer to 2, but you're not quite there. But the honest to God simplest and most like robust method when it comes to polynomials is to just plug the value. So plug the value that you're approaching. So I'm gonna write it here, the limit as x approaches 2 of f of x is equal to, well, this is the limit as x approaches 2 of x squared, and I just plug 2 inside here into the function. I find f of 2, so that is 2 squared, and that's 4. And you'll notice that, okay, let's pick a sample point over here, maybe even 1, and then let's pick 3. And I plug this here. I get 1 squared, which is 1, and then 3 squared, which is 9. And then as I get closer, let's say 1.99999. Well, that's gonna give me a corresponding y value, like, which is 3.99999 or 2.9999. That's you can plug it into your calculator, and then it'll like tell you that as I get closer and closer to 2, either coming from 3 or coming from 1, like coming down from 3, like going below 3 and then towards 2, or going above 1 and then, you know, adding like a 0.001 something, like a very small value basically, and getting closer and closer and closer to 2, you'll notice that the function does not exceed 4. It does not give a 5. It doesn't give a 4.1. It doesn't give a, well, usually it would give a 4.1 if you're someplace here between 2 and 3. But generally, it does not give a value that's greater than 4. So we can say that L is equal to 4. And that's your limit. Okay, let's try a more complex limit to solve. Okay. Let's try this one over here. X squared plus 4x plus 4. And let's say evaluate that for x equals 1. And okay, here's a shortcut that I want to teach you guys. When you're given a polynomial and you're asked to find its limit as x approaches 0, if all of those, or if all the terms, so each of these things, each of these parts that get summed together, we call them terms. If each term contains the independent variable, which is x in our case, it can be u, it can be v, it doesn't matter. If it has the independent variable, or if every term has an independent variable, and you're trying to find its limit as x approaches 0, it's immediately 0. Alright, you can immediately plug there 0 without even having to plug it into the calculator. But in this case, it's different because I have a constant over here. I have 4, and it doesn't have an x attached to it. And I'm trying to find the limit of this function as x approaches 1. And again, same procedure, just plug 1. So that's 1 squared plus 4 times 1 plus 4. And that works out to be 9. And you'll see that as I get closer to 1 for this function, it would look somewhat like x squared, but it's shifted around. Okay, so you guys will find out that, oh well, it gets closer and closer to 9. It would be like 9.00001 or either 8.9999999 as you get closer and closer, right? But you see that the values never exceed 9. No matter how close you get to 1, it never goes beyond 9. Okay, so here's one wherein you would use a little bit of knowledge from our trigonometry lesson and maybe even trig identities. So how about the limit as x approaches pi over 2 of sine x? Okay, so recall that sine is an uneven function or an odd function. So it goes like this. And the point wherein it intersects the x-axis is precisely at pi, x equals pi. And when it also intersects in the negative value, that would be negative pi. Okay. Yeah. So we're now looking for pi over 2. So that would be strictly between 0, the origin, and pi itself. So this would be pi over 2. And you know that the extremes, or at least the function sign, does not exceed 1, or it does not go below negative 1. So the highest value that sine can give you is 1, and the lowest value it can give you is -1. In this case, now we're trying to find the y value at this point. So we just evaluate it, and we find that sine x, or the limit of sine x as x goes to pi over 2, well, you could say goes to or approach, it's the same thing, is sine of pi over 2. And that works out to be 1. You guys can correct me if I'm wrong on this because my knowledge on trig functions are a bit rusty. But there's that. A more complicated example. But here's the thing wherein our procedure fails, right? Here, we cannot keep plugging x and then hope for the best. Okay. So here's a counter example. How about the function 1 over x? It would look something like this if you graph it. So the asymptotes of these functions, so asymptotes are basically the lines or values wherein this becomes infinite. So the asymptotes are the x and the y axis themselves. So 1 over x, for every x value, it gets closer and closer. As I get closer to 0, it gets closer and closer to the x-axis, but it doesn't quite touch it. And likewise, if I go towards here, towards infinity, it approaches, no, I meant the y-axis. It approaches the x-axis in this case, but it doesn't quite get there. But the limit usually tells us that it does not go below 0. Okay, and we'll discuss that when we talk about improper limits. Okay, so let's find the limit of 1 over x as x approaches 0. And you guys can probably already see from here, oh, that looks like a 1 over 0, and a 1 over 0, what? That's undefined. If I try to plug that into my computer or my calculator, it gives me an undefined. And that is true, because 1 divided by 0 gives me an infinite amount of values, right? Divide 1 by 0, you can get 2, you can get 3, you can divide it into, like, if I want to divide 0 into 1, or like if I want to divide one value into 0 boxes, or say I want to divide one apple into 0 boxes, there's a lot of boxes I can make, and it would still give me 0, right? So I can put one apple in, I suppose, an infinite amount of boxes, and it would still give me this, like, it would still give me valid answers. So it's indeterminate. So this gives me a 1 over 0 if I try my conventional method of just plugging and chugging, right? So that's the thing about here. And the thing is, okay, even if I try to find its limit, right? Okay, it may not approach, or I may not find, or it may not be defined in this case, but maybe I can find a value wherein it doesn't, like, it doesn't go beyond, maybe infinity. Because look, as I approach the origin, it goes up, 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 the y values shoot up. So maybe L is infinity. But here's the problem. Look at how I approach it now from the left, from minus infinity. If I get closer and closer from minus infinity to 0, it goes down. It's going down, down, down. And you can verify this, right? You can plug smaller and smaller values, like 1/2, 1/3, 1/4, 1/5, 1/6. You can put 0.000001 and it will give you a very big value, right? And it's seemingly boundless, so you can say it's just infinity. But the problem with that is that when I approach from the left, it approaches negative infinity. I have negative big values, so it shoots towards minus infinity. And here's the thing about limits, right? So let's go back to my example a while ago. Focus on the thing, not my thighs. Okay, so right, when I approach something from the left and the right, they agree. They approach one singular point, right? And that's, we're gonna make that more formal or more definite when we talk about continuity, which is right after I give an introduction to derivatives. So, or actually, right after this video maybe. So, you notice that these two, as I approach them, they approach one value. And that's a very important rule when it comes to limits. That limits are only one value. If I approach a function from the left and the right, and then I get two different y values, like say it looks like this, there's a gap or a jump, then practically the limit does not exist. Overall, the overall limit does not exist. But there will be a sort of breaking down that we can do of a limit to show like maybe it can approach this value, maybe it can approach that value, but separately, not together. Because on its own, when we're talking about limits, we're approaching from both the left and the right. But we will see in the next lecture or in the next video that I can restrict that. I can split it in half and say and only consider approaching it from one side. And that's called one-sided limits. Or left-handed or right-handed limits. Alright, so let's go back to our example. So in this case, note like remember that a while ago I said it doesn't approach a definite value. It doesn't approach one point. If it were the absolute value of x, if this were the absolute value of x, that means I would get only positive numbers because absolute value of a number is just its positive version, right? It's distance from x, and distance can only be positive. So it would be going this way and then just disregard that part. It would go this way, and yes, it would have a definite limit, which is infinity. It may not be finite, but at least there's a limit. But in this case, because there are two different values, our function approaches as we get close to 0, it's called undefined or does not exist. Does not exist. Or just write D and E when that's the case. But if I can practically talk about one-sided limits now. So if I approach only from the right, disregarding this part, it only goes to one value, which is infinity. So we can say that the limit as x goes to 0 from the right. So here's a little bit of notation or terminology. When I approach a value from the right, I put a plus on the top. If I approach a value from the left, I use a minus. So 1 over x, that's positive infinity. Because it shoots up, 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 and I get bigger and bigger positive values. But if I approach it from the left now, disregarding this part now, and I go this way, down, 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 it keeps going down and down and down. So this time I write 0 minus. This is notation, okay, to say that I'm approaching the function from the left, and for this case, I'm approaching the function from the right. I'm getting close. I'm not the function, but the value 0. So the x here is this time minus infinity because I get bigger and bigger negative values. And you know that as I go here, I get bigger, positive values, negative values, negative values. Okay. So that's that. So this is one-sided limits. And here's another application. Consider the sine function. Sine of x. Or SGN of x. I don't know what other or something is called the signum function, because in the book that I learned calculus for the first time, in Earl D. Rainville's book, Differential and Integral Calculus, 6th edition, he called it the signum function, but it's all sometimes I've seen on the internet that it's called the sine function, but it conveys the same idea, which is to give you the sign of a number or of an input. It basically tells like if it's positive or it's negative, if it's +1 or -1. Like say if it's a -1, that means if it's a negative number, that means it's multiplied by -1. So that means the output will be -1 for all those values. And if it's positive now, that means it's multiplied by +1. So that means it's 1 for all those values. So let's graph that. So the only one that doesn't have a determinate value here is 0, because I can multiply -1 to 0 and -1 to 0, and I would still get 0. I wouldn't have a -0. I wouldn't have a +0, because that's just 0. Because no matter if I minus 0 from itself, 0 minus 0 or 1 minus 0, that just gives me the same thing. Same thing with adding. So it doesn't matter if my 0 is negative or positive. So there is no definite value for here. So in that case, because that value doesn't quite exist, we put a hollow dot, right? to say that it doesn't exist at that point, or the value does not exist. But we can find the limit. That's another advantage of limits, is that even though I can't find the y value at a point, I can at least try to find algebraically or approximately what the function does not exceed, or the value of the function does not exceed as I approach that certain x value. Even if I may not be able to plug and chug, like I would get something like 1 over 0 or 0 over 0, which is really bad, maybe I can try to find a value that the function does not exceed, right? And we will see that later. Okay, so this is the sine function or signum function. So this is positive 1,